This episode of Science Scout takes it to the next level. Before we start, please make sure you subscribe to this channel and hit the bell to get notified about our new upcoming videos. Today, we would be discussing about a battery that possibly could change the world, a battery of the future. Most batteries are made up of either solid-state electrodes, such as lithium-ion batteries for portable electronics, or liquid-state electrodes, including flow batteries for smart grids. Most industry executives and researchers argue that lithium-ion batteries will pave the way to future of solar storage. Take, for example, Tesla's Powerwall, which uses rechargeable lithium-ion batteries for stationary energy storage that can power your home through the sun's rays. And according to Grandview Research, the lithium-ion market is projected to be worth $93.1 billion by 2025. But a novel concept in reversible chemical to electrical energy storage, known as liquid metal battery, could change all of this. This battery system is much different, as it is the only battery where all three active components are in liquid form when the battery operates. So, what exactly is this novel liquid metal battery? Liquid metal battery is a new type of battery in which both electrodes and the electrolyte are in liquid state. It was designed to provide battery storage to compensate for imbalances in electrical grids. It was invented by MIT professor Donald Sadoway, and his then graduate student David Bradwell designed the first proofs of concept using antimony and magnesium with a salt electrolyte. In 2010, they formed a company, which has been funded by Bill Gates, Khosla Ventures, and energy company Total. To form a battery pack, 54 cells are stacked together. 16 packs, which the company calls an Ambry core, will provide 200 kilowatt-hours of energy storage. When several of these storage units are strung together in a full-size unit, Ambry anticipates it can provide 500 kilowatts of power for 4 hours. The liquid battery comes with a wide range of benefits that sets it apart from the commonly used lithium batteries. It's designed to produce lower operating temperatures and more stored energy at a lower cost. Liquid metal battery has the potential to revolutionize energy storage. But how does the metal liquid battery actually work? Classical batteries typically have solid electrodes and a liquid electrolyte. But the liquid metal battery is composed of two liquid metal electrodes, magnesium and antimony, which are being separated by a molten salt electrolyte. The upper electrode is a low-density liquid metal selected from the electropositive electron donor elements, and the lower electrode is a high-density metal chosen from the electronegative electron acceptor elements. A medium-density molten electrolyte is sandwiched in between both electrodes, and this allows metal cation transport between the anode and cathode. Because of the different densities of the electrodes and electrolyte, and also their levels of immiscibility, when heated to liquid form rather than mixing, they self-aggregate based on their levels of density and float into three distinct layers. However, the electrolyte can dissolve both metals. This removes the need for a separator as opposed in conventional energy cells. Discharging. Magnesium is an electron donor, and the discharge cycle begins with enough electrons on the anode supporting an electric field across the cell between the anode and the cathode. During this discharge, the magnesium anode is consumed as the magnesium ions migrate from the upper magnesium layer, seeping through the electrolyte to form a magnesium-antimony MgSb alloy, with the antimony in the lower layer increasing its volume. Any excess electrons on the anode flow through the external circuit to the cathode, where they neutralize the positive charge of the cations. The external current flows in the opposite direction from the electrons, which is from the cathode to the anode, thereby delivering power to the load. Charging. In order to charge the liquid metal batteries, power from an external source drives electrons in the opposite direction, and at the same time pulling magnesium ions from the magnesium-antimony alloy and redepositing metallic magnesium back into the top layer, thereby returning the system to its three distinct liquid layers. In order to keep the active metals and electrolyte in active state, liquid metal batteries have to operate at an elevated temperature, and this is achieved by self-heating during charging and discharging, resulting in a low-cost and long-lasting storage system. When a liquid metal battery operates at room temperature, there exists potential energy between the electrodes, which creates a cell voltage. The cell voltage is determined by the difference in electronegativity of the metals, which relates to the difference in their Fermi energies. The larger the difference, the greater the cell voltage. These electronegativity and Fermi energy differences were paralleled by the respective densities, a feature which fortunately enabled the requirement for liquid density differences and layer ordering to be concurrently satisfied. Now that we have a clear understanding of the metal-liquid battery structure and how it works, let's look at some of the advantages and disadvantages. Liquid metal batteries offer us immense advantages, one of the most important being that they have a very low cost. For example, Ambri cells utilize electrodes comprised of commodity materials that cost a third of those in NMC lithium-ion cells. The manufacturing of Ambri cells is far simpler and requires a third to a half the capital expense per megawatt hour of production than lithium-ion. This is largely due to the fact that most of the materials being used are earth-abundant and way cheaper than other materials. Furthermore, Ambri-based systems do not have cooling, fire suppression, or module and rack-based BMS equipment, as lithium-ion systems require. For these reasons, Ambri-based systems are projected to cost 30 to 50% below equivalent lithium-ion systems from 2022 to 2030, even after accounting for the aggressive cell price reductions that are forecast for the incumbent product. Lithium-ion batteries are projected to drop in price from current levels to less than $100 per kilowatt-hour at some time in the mid to late 2020s. Even compared to this low future lithium-ion price of $100 per kilowatt-hour, these energy storage systems will be 70% more expensive than Ambri-based battery systems. Also, the natural self-segregation of the active liquid components enables a simpler and low-cost cell fabrication when compared with other conventional batteries. Another advantage of liquid metal is that overall, liquid metal batteries are more suitable for large-scale electricity storage compared to the popular lithium-ion batteries. The liquid metal battery, though heavy, it cannot burn and neither does it fade with use. Lastly, when compared to its strong competitor, lithium-ion batteries, it seems that liquid metal batteries are more suitable for large-scale electricity storage. Despite these advantages, liquid metal battery has its disadvantages. The biggest disadvantage of this technology is the elevated operating temperatures, which are generally less than 200 degrees Celsius. Also, there are 3 liquid layers that make operation of the battery very sensitive to motion, and this becomes very dangerous when the liquid electrodes touch, which leads to a short-circuited cell and fleeting heat generation. However, according to Ambri, at room temperature, Ambri's cell is non-conductive and its active materials are solid metals and a solid electrolyte. Upon heating to 500 degrees Celsius temperature, Ambri-based battery systems operate at maximum performance level, no matter the external temperature, and require no power-hungry air conditioning. Ambri-based systems generate their own heat during use, thereby eliminating the need for auxiliary power for temperature control. These systems like to be used. A full charge-discharge cycle at least every 2 days will keep the system at its operating temperature, and higher duty cycles will not increase degradation. I have spoken so far of advantages and disadvantages, but now I want to talk about the materials cost and abundance. Metals. The use of antimony, Sb, as the positive liquid electrode in a liquid metal battery offers a low-cost chemistry, below the threshold cost required for broad-scale adoption of a large-scale electricity storage technology. Antimony could potentially drop the cost of the active components by a factor of 5, while providing similar voltages for analogous chemistries. Molten chlorified salts, such as magnesium chloride, potassium chloride, and sodium chloride, are suitable as the electrolyte, providing high conductivity, a suitable density and liquid range, and stability with reactive metals. Now, let's talk about bringing liquid metal batteries to the market. Grid-scale storage is a key target for liquid metal battery technology and its energy storage capacity. Ambri has a 1,000 kilowatt-hour capacity, 250 kilowatts output, 500 to 1500 voltage, response time less than 500 milliseconds, and exceeds 80% of DC efficiency under a wide range of use cases, which fits into and can be delivered in a 10-foot shipping container. Ambri, a liquid metal startup, signed a joint development agreement with NEC Energy Solutions. The agreement will see NEC develop and design an energy storage system based on the liquid metal battery technology of Ambri. NEC will also employ its proprietary Eros energy storage operating system and controls in order to optimize the system of performance of the Ambri-based energy systems for NEC customers that could include utilities, independent power producers, IPPs, and other project developers. Ambri itself has raised over $50 million to further develop and improve on its liquid metal battery technology. They claim that when batteries are tested in the lab, they are often cycled 12 times per day. This allows researchers to achieve 1,000 cycles in just a few months. Researchers are often tempted to extrapolate this cycle life to predict a lifespan. For example, if a battery maintains 90% of its capacity after 1,000 cycles, then it should maintain 70% of its capacity after 3,000 cycles. And if the battery is used just once per day, then 3,000 cycles should last nearly 10 years. In addition to that, some extensive laboratory testing on over 2,500 cells with a cumulative test time of 600,000 hours and 100,000 cycles shows that the all-liquid cell design avoids the main failure mechanisms experienced by solid components and other battery technologies, which enable their systems to have a projected lifespan of over 15 years with no degradation in performance. The liquid metal battery provides an innovative approach to solving grid-scale electricity storage problems, and its capabilities allow an improved integration of renewable resources into power grids. Are you interested in learning about biofuels, their history, classification, types, uses, production, and the cost of production? Watch the next video. Before we conclude this amazing video, let us know what new things you learned about metal liquid battery. Comment down below and enlighten us with your thoughts on this. Also, subscribe to our channel and hit that bell icon to get notified about our new upcoming videos. With that being said, we've reached the end of this video. Thanks for watching it. We'll be back with more interesting videos. Till then, take care and never stop learning.